Hi, welcome to a series of webinars on optical network technologies and protocols. This is your friend Brahmanand in the journey of learning. The main objectives of this series of webinars is to discuss about SDH Sonnet, WDM, OTN, element management layer, network management layer, and project management linked to these technologies. Today's topic of discussion is layered architecture of SDH. SDH has typically three layers. One is physical layer, the second section layer, and third path layer. The physical layer is involved in converting the data or the signal from electrical domain to optical domain and feeding the data into physical media like optical fiber. Multiplex suction layer and regenerator suction layers are involved in managing the inter-NA communication. As we know, multiplex suction layer is between an SDH multiplexer to cross connect or from between two multiplexers, and similarly regenerator suction layer is between two regenerators or between a regenerator and a mux or a cross connect. And the path layer is involved in managing the client signals from source to destination. So these are the typically high-level view on layered architecture. Let's understand a couple of terms being used in SDH which would help us in understanding the layered architecture in a better way. The trails and TTPs. What is trail? A trail is a pipe between 2 points. If suppose I'm feeding some data here and I want to take out the data here, then I put the data in a pipe. This pipe between 2 points is called as the trail, and the endpoints of this trail are called as TTPs. Trail termination points. Typically, we have been using trail in a very generic form. A trail has got two types of it. One is section and the second one is path. Section is a trail in section layers, and path is a trail in path layers. Let's understand what happens during a data communication. What happens at source, that is at the input side, and what happens at the output side. Normally, if this is my pipe, I'll feed my client signals into pipe, and I'll add overhead data with the client into the trail. And at the output side, that is at sync, this overhead which we have added at source is processed and the required client signal is taken out. Now, what is overhead? Overhead is the data used to manage the trail. If my data traverses in many directions and reaches the destination, I need to manage my data from source to destination. That is why I had overhead. And the processing at the output side of overhead is used to raise alarms if found in my path layer and monitor performance if there are any errors across my path layer for my path trail. I should be able to monitor the performance of my data for any bit errors or whatsoever. That is the reason why I also need overheads. And I should be able to allow communication between the network elements itself when data is moved between network elements. So I need overhead for communication between the network elements. Please make a note one thing very clearly, that overhead is always processed and removed at TTP. If no TTP, no overhead. We don't add overhead anywhere else apart from TTP, and we process the overhead only at TTP. Overhead and interoperability. Assume, as we discussed in any other webinars, I have my payload and I have my overhead. So now you know why we had overhead. Now these overheads have to be defined through some standards. If they're not defined through some standards like G707, then if every vendor or operator uses the definition of these bytes differently, then it is very difficult to have interoperability between multiple vendors' equipments. So standardization of overhead is very important, which is being supported through standards by I2ET for SDH. Please make a note that I can have multiple client signals to my trail termination point with a single processed overhead before it's put into my trail. This concept would be very useful when we discuss about virtual concatenation in a different session. Let's understand what happens in terminal multiplexer. We know that we have one high-speed signal which gets terminated to my line terminal multiplexer, and low-speed signals are removed. Now let's take for an example, if this is STM1, we know that there will be one VC4. Now, as we discussed, if it is a trail, VC4 trail, then it has to have a trail termination point. So we have one trail termination point. Let's assume that we have mapped 34 Mbps client signal to VC4. Then it means that I would have mapped 3 such 34 Mbps client signal to VC4. It means that I should have 3 VC3s, VC3 number 1, 2 and 3. And from these VC3, I will take out my 34 Mbps client signal. It means that in this particular example, I have one VC4 trail termination point and 3 VC3 lower order trail termination points. So this is lower order trail termination point number 1, 2 and 3. So we have in totally 4 trail termination points in this example. Let's see what happens in ADM. Let's take for an example. We know that in ADM there will be 2 high-speed lines, and there could be n number of tributary signals. So now let's say that this is an STM1, so we will have 2 VC4 trail termination points terminated into my ADM, and let's say that we know that VC4 will have 3 VC3s trail termination points. Assume that if I want one of the 34 Mbps signal to be made pass through, and I want to take out only 2 34 Mbps signals out of this VC4, it means that I would have only 3 trail termination points at this particular trail, and I would not have 4, as we discussed in an example in the last slide. So this will be made as pass through. So there will be a direct cross connection, so there will not be any trail termination point. It means that the overhead would not be processed for 34 Mbps, that particular TTP at this particular ADM. Whereas we would process VC4 higher order path overhead would be processed for VC4, as well as lower order path overhead or path overhead for these 2 VC3s would be processed in this ADM. Connection termination points. So when a trail is terminated, the trail it contains are represented by connection termination points. Say for example, I have a VC4 trail, and the VC4 trail termination points can have 3 connection termination points. These 3 connection termination points are called as AU4 CTP, AU4 connection cross connection termination points. So if my trail is VC4, then my TTP is called as VC4 TTP and CTP is called as AU4 CTP. Similarly, for VC3 trail, TTP is VC3 TTP and CTP is TU3 CTP. Similarly, for VC12, it's VC12 TTP and CTP is TU12 CTP. In this example, if STM N fiber contains, let's say, N into AU4, then a VC4 CTP contains TU12 CTPs, and it also contains 3 AU4 CTPs. But make a note that this can be processed if I have, in this example, let's say I have 140 Mbps one client signal, and let us say I have 3 34 Mbps signal, then I could have that 140 Mbps signal could be terminated at this particular VC4 TTP, and my client data can be taken out from this AU4 CTP, and similarly my 34 Mbps can be taken out from this particular TTP. Suppose the mapping is TU12, then I will have TU12 as CTP, wherein I can have once I get it terminated, then I will have 21 TU12 CTPs here. Cross connections. A cross connection connects two signals together. It means that if I want to route my data, say for example through an ADM, however I want, so because of this cross connection, I can route my pipes based on my requirement. So I can make the cross connection using the connection termination points of my trail termination points. For a CTP to CTP connection, I will the trail is whatever is the trail of my whatever it could be the trail. Say for example VC4, when I terminate this, I will have VC12 CTP, and once I terminate that, I will get TTP again. So through which I can make the cross connection. So please make a note that there is no overhead which is processed at connection termination points. CTP to CTP connection. So once I have a termination done for a VC4, as I would have T12 CTPs, I can make a cross connection directly from T12 CTP of one particular trail to T12 CTP of another trail which was terminated in, say for example, in an ADM. A trail is terminated with a TTP. A TTP, trail overhead, is processed. After a TTP, a CTP is present for each client signal in the trail. So client signal is present in connection termination points for each trail. No overhead is available at connection termination points. So the connection between TTPs and CTPs are called cross connections. Is any can repeatedly multiplex the same signal. It means that if I am putting my VC12 into my VC4 and VC4 into AU4 and AU4s to multiple other administrative unit groups or whatsoever, then it means that any as multiplexing the same signal a couple of times within the any. So let's take this example wherein this is my client VC12 TTP and this will ride on my VC4 TTP. So in this there is a client server relationship established between my VC12 TTP to my VC4 CTP through the contained CTPs. Eventually, this will be having a server which is physical TTP on that particular port or a trail termination point which is linked to my physical layer. So clearly this indicates that within any there is a client server relationship between the layers. Multiplex section layer. The multiplex section layer monitors the inter-node connection for false and performance data. When any issue or any traffic affecting problem happens between say for example between two ADMs within a multiplex section, an alarm is generated. So this particular information would be communicated to the user through the network management layer functionalities, which we're going to discuss it later. So multiplex section, it keep monitoring the faults within the multiplex section and keeps monitoring the performance data which is communicated to the end user and the operator who is managing the network. Regenerator section layer. We know that a regenerator is required to boost my signal, amplify, retiming, and also if my data need to be transmitted for a very long distance, I need my regenerator. So it is very useful not just to manage the connection between a terminal multiplexer where the signal get added and where the signal get dismantled, not just managing these two but also managing this particular section which are called as regenerator section would enhance the probability of managing the network in a better way. So we can identify any fault or performance issues during at this regenerator sections and take corrective actions. So that's the use of regenerator section. Please make a note that regenerator does not change the data related to multiplex section layer. So multiplex section information is transmitted as pass-through data in regenerator. This is typical physical and logical view of what happens in regenerator and multiplexer. Let's take for example some connections is established which goes between a terminal multiplexer to another terminal multiplexer via regenerator. Then what physical layer does is it puts the signal onto the fiber. The regenerator removes the signal from the fiber and puts it back, and so the physical layer of the regenerator puts it back again, which reaches my destination node. So what happens in this case is whenever a terminal multiplexer puts multiplex section overhead and regenerator section overhead with the claim data, at regenerator it processes only regenerator section overhead. It based on the data alarms or performance data, it reconfigures the region intersection overhead and puts it back, and the same data goes to the next terminal multiplexer. We can see it here that the multiplex section overhead, which was placed by a terminal multiplexer at this source, is not processed at this regenerator section. Instead, it is directly processed at destination mux. If we consider this as a multiplex section, it is not processed in this regenerator. Instead, it is only processed at the end terminal multiplexer. So just to quickly summarize, in the regenerator section overhead is terminated, multiplex section overhead is not terminated, whereas in all other building blocks of SDH, both the overheads are processed. This is one of the functional view of what happens in my regenerator section and multiplex section. See, multiplex section and regenerator section layers, they are no way different from path layers. I mean, all these functionalities almost the same. So we know that every data can flow only in a trail. So it should start with a trail termination point. Say for example, in this regenerator, it gets terminated by a TTP, and a regenerator section TTP will have multiplex section CTP, which will get cross connected to its own multiplex section cross connection termination points, and the data flows again. So it is passed through. Regenerator doesn't know what is the data flowing in the multiplex section between two multiplexers. So it doesn't really care what is there in the multiplex section overhead. Instead, it only reconfigures, realigns, or processes only regenerator section overhead. So as we know, regenerator section TTP contains multiplex section CTP, which is getting cross connected at regenerator and made as pass through. So layers across network. So whenever tributary signal is put into a node, as we discussed in one of the slides, that it can undergo a multiple muxing within an NA and reach a TTP. So it can, if suppose this is E1, then I would have AU4, it can sit in my AU4 CTP, and finally it can sit in my VC4 TTP, and then sit in maybe higher order STM N, and then keep going in. I mean, so the same process of demultiplexing happens in the destination node. So just to summarize the SDH layers, the physical layer is involved in converting electrical signals to light or radio signals, in the case wherein we use microwave as the physical media. So it can also convert to radio signals. So physical layer is responsible for putting signals into a physical medium. So it can be optical fiber or microwave radio. And section layers, as we discussed, they are the ones who manage an inter-NE connection. So I mean, it all depends on the network topology. So section layers have different functionalities to play, which is based on network topology. with a regenerator or without regenerator, and so on. So they have their own overhead, as we discussed in the SDH frame. And so when we discuss more about the overhead in a separate session, we will understand the each and every byte in the section overhead, which demonstrates or which functions and which will enable the operator to efficiently manage the section layers. So just to summarize, its section layers are mainly helpful for framing of the STM frame, a synchronization between network elements, error monitoring between the network elements, and sharing the performance data if there are any bit errors, and data communication channels which would be used for managing the entire network from network management layer. So, and that will also be supported by these section layers. And section layers also very helpful when you want to protect your paths. So protection is one of the key function of section layers. The path layer manages the client signal from end to end and supports error monitoring from source to destination. And we have higher order and lower order path layers. Higher order path layers for VC3, VC4, and lower order path layers for VC1 to VC11 and VC2. And each path layer has its own overhead in SDH frame for monitoring the data from end to end. So this is an high-level summary of SDH layers. In a different session, we're going to see suction overhead and path overhead functionalities. That's it for today, and if you like my webinar, please subscribe to my channel and click on like. And if you have any comments, please write down your comments. Thanks for watching. Thanks for your time.